class. Good morning. Looks like I'll be teaching virtually today, so let's go with it here. We're going to go into 2.5. We did the beginning of this lecture last time, and so I'm just going to quickly recap for you, and then we're going to slow down a little bit here as we do the rest of it here. So we are not talking about vectors. This guy, vector, we're talking about vectors. So let's keep on going. The question is, what are we talking about? That's what we're talking about. We're talking about vectors. Vectors is a ray that represents magnitude and direction. And so which direction the arrow is pointing is one thing, and also the length of the arrow itself is also one thing as well. And so this is notes from last time. So if I am pointing down, usually that represents south. So this arrow is representing 50 miles per hour due south. If I shorten it by half and I draw an arrow like this, that means it's only 25 miles per hour. Still due south, still same direction. And if I change my directions, then I go this way here. So 25 miles per hour, then I switch it up, and then it's going to go due north at this point. So let's go with it. There it is. Some notation. We also did this last time here. So notation, a vector is represented by a capital letter, and it's always bold, as we'll see in the notes as well today here. And different textbooks use different ways here. So if you just have a capital V, usually V is given as direction, or as for vectors. Sometimes a V with a arrow on top. Sometimes it's the A and the B. It's two letters signifying which part of the figure you're dealing with, and then they have direction that way. So that's a vector. A scalar. Scalar is pretty much the distance or how fast something is moving here. So it's a lowercase letter, or sometimes bars around the vector itself. So you could just use x as a lowercase x. You could also use, it looks like absolute value bars because we have the same thing. Again, it's the running out of notation in mathematics here. So the vector is given as v. We put these bars around it to say, look, I'm not looking for the vector itself, I'm looking just for the magnitude. All right, don't need to copy all this down, but you guys can read it here as I read it. Many of the vectors that describe the world around us have both magnitude and direction, while others only have magnitude. So it just says, hey, that car was going 50 miles per hour. And it's not giving you direction. Okay, quantities that have magnitude and direction are called vector quantities. Well, quantities with magnitude are only called scalars. All right, I don't expect you to write all this down. Just kind of think with me. It is inside the textbook as well. So one way to represent vector quantities geometrically is with arrows. As we've seen already here, the direction of the arrow represents the direction of the vector quantity, and then the length of the arrow corresponds to the magnitude. Let's take a look at some. And I think we've covered this as well. Equality of vectors. What does it mean for two vectors to be exactly the same? If they're going to be exactly the same, they're going to have the same exact length as well as the same exact direction. And so here's geometrically, v1 is the same as v2. Notice it has the same exact direction and the same exact length. V3 is not the same in any one of those. If you wanted to show that algebraically, you would do this. You would say V1 is equal to V2. Again, direction, magnitude, the same. And then we also say, look, V1 is not the same as V3. V2 is not the same as V3 as well. All right, again, given last time here. One last thing is the zero vector. The zero vector has a magnitude of 0. It's not defined direction. It's pretty much at the origin, stays at the origin. And so, given that, okay, I think we're ready. So this is where we left off here. Addition and subtraction of vectors. Let's add these guys together. Let's subtract them. Let's see what that even looks like as we put them together here. And so now we have two different vectors. I'm going to represent it by two different letters. So notice the capital U, the capital V right here. And I'm going to write it just like I do math. I'm going to write U plus V is just fine. With the plus sign, get some vocabulary here. It's called the resultant vector. But just for you guys to understand, whenever we add vectors together, we always go from tail to tip. So if I'm going to add U, I'm going to place U down here. And then I'm going to place V right at the, I'm going to use its tail right at the tip of U, and I'm going to correspond it to wherever it is. So it's kind of just moves it across. And so I have U plus V. We should note that you could go the other way as well. And so you could say that this is V plus U, and that's going to give you the exact same distance here, just like in mathematics. U plus V, V plus U would still give you the same exact resultant vector either way. So that little red one right there, that little red one is the addition of both vectors at the same time. All right, so what are we talking about when we talk about vectors or in real life? Well, there's lots of forces acting upon things. And so let's take a car, for example. So we have the car itself has weight, so there's a force that's pressing down because of gravity. We have the reaction force, which is going against the gravity because the car is not falling down through the street, so there has to be a force that's actually keeping it up instead of making it fall through the concrete. Then we have the drive force. The car is going forward at this place. It's going this way. We have friction, which is on the tires. It's making the car stop, really. And then you have air resistance. It's also making the car stop. So all these forces are acting upon a car while it's traveling. Another one real quickly here, as far as airplanes are concerned. We have thrust, which is how fast the airplane is going forward. We have the weight of the airplane bearing down on it. We have lift, which is going up. And then we also have something called drag at the end. So all those, again, four forces acting upon an airplane as it flies through the air. All right, back to Earth. How about if we have a box? A box just standing on an incline. And so all those things right there here. So we have something called a normal force. It's just the exact opposite of the gravity pushing down on it because it's staying up. We have gravitational force going down. We have any external forces placed on the object, and then we have the static force, the fact that it's sitting on something, so therefore it's not letting it slide, or maybe it's sliding a little bit here, but there's friction between the box and whatever it's sitting on, and then usually we have some kind of angle. Okay, keep on going. So addition, subtraction of vectors here, visual representation, here it is, just for you guys to see it. If I was going to add U and V together, I'd put down U first, and then I'll place V, trying to give the same magnitude, trying to give the same direction. I'd put a tip to tail, and there's my addition of U plus V. If I were to subtract these two forces, or subtract V from U, I would have to change the direction on V. So notice the length of V does not change, it's just the direction. The direction now is exact opposite here. So if I was going to say U minus V, I'd still place down U over here on the side. Except now instead of going this way, going down towards the right, now I'm going to go up towards the left for minus V. And there's my resultant vector right here. So now I kind of went a different direction than the previous slide. All right, let's get to some example problems here. Hayden, all right, is on a boat. Did not know you owned a boat. That's cool. And is crossing a river that runs due south. The boat is pointed due east and is moving through the water at 10 miles per hour. That's cool. The current of the river is a constant 5 miles per hour. Find the actual course of the boat. So Hayden thinks she is going straight, but that's not the case because she's going straight across and the current is actually pushing her down a bit. All right, he is on, let's see, find the actual course of the boat Hayden is on through the water to 2 significant points. I think we can do this. Let's see if we can draw this. So again, don't want you to write every single word out. Maybe write down the important words of example 1 out, or just draw the picture. And let's see what happens there. So first for direction, let me give you north, south, east, west. So at least I know which way we're headed, which way we're going. And she's crossing due east. So that means she started on the left side. There's my water. There's my little river running south. So I have one side of the river, the other side of the river. She'd have to start here if she's going east. So there's my little dock that she started on. And let's go with it. I'm going to go like this and kind of represent, for me, that's going to be my 10. 10 miles per hour is going to be that right there. And I might as well write it in. Then I have the current of the water going this way, and I'm going to draw it about half the length of the previous one. About there, 5 miles per hour. All right, resultant vector, if you haven't drawn it already, there it is. Draw that one. And we want to find the actual course of the boat. So I need direction and magnitude. I need both. So let's go with it here. So let's go with magnitude first. That's pretty easy. If you guys noticed on the previous one, that was a right triangle. And right triangle has a Pythagorean theorem associated with it here. So I can figure out the magnitude pretty quick. How about put in 10 for A, 5 for B. I'm going to square those. That'd be good to square them. Square, square, and square. Got Christmas colors here, green and red. All right, it gets me. Oh, I squared. Looks like I did square the C. Forgot to square the other ones here. That's 100 plus 25. 125, and then we're going to factor this down just a little bit to get our exact answer. How about this? This is going to be 25 times 5. So I have perfect square of 25 going out, and then I have a 5 left over. That's going to be C. And in these problems here with physics and stuff, we don't do exact answers like we do in mathematics. We normally round them off to a certain spot here. And you know what? As I'm looking at my answers here, I round them off to one digit here. That's okay. Let's go for it. Now we're looking at an angle. How do we find that angle? How do we find that angle? So let's see, it was a triangle. I got 10 on the top. I had 5 on the side. The right angle turned right there. That's where the boat is hitting the current of the river. I have my angle right there. And so which trig function gets me what I need here? Looks like it's opposite and adjacent. You guys are going to know this very well. It's tangent. Tangent of theta is equal to opposite over adjacent. And in order to get angles, we have to do the inverse of tangents. Inverse of tangent of 5 over 10. Grab your calculators here. And punch that in. Hopefully you got that here. Make sure you are in degree mode on the calculator. Go from there. So as you punch that in, you should get an answer of, I think it's 26.6 degrees. Okay, so now let's figure this out. So that means I have this. I have a triangle. Now let's add in a few things here. I'm going to add in now the directions here. So now I have north, south, west-east. And I know this angle here is 26.6 degrees. Since we're going south, that means I'm going to have to get this angle here. So I'm going to have to get the complementary angle. I think I know how to do that. Complementary angle is going to be 90 minus 26.6. In fact, I'm going to let you guys do that. Why do I do all the work here? 90 minus 26.6. I'll let you guys do that just for a second. All right, second is gone. So I'm going to have to borrow here. How about a 4 on the back end? 9 minus 6 is 3, and 8 minus 2 is 6. And I'm done. There it is. Are we good? So let's write this out. In fact, you know what we'll do? I'm not going to do the significant digits as that important here. I am going to just round this off to the nearest tenth. So 11.2. So 5 times the square root of 5 should give you 11.2, and that will be our miles per hour. And let's go with it here. So the answer is Hayden is heading south 63.4 degrees east at 11.2 miles per hour. All right, good job. All right, with that, let's jump to example 2. This may be a little bit more violent here. Grant, I never knew you act as a human cannonball sometimes. So Grant is shot as a human cannonball with initial velocity of 67 miles per hour, angle of 60 degrees from the horizontal. Cool, 2 things here. Find the magnitudes of the horizontal and vertical vector components of the velocity vector. Whoa, a lot of stuff here. Let's see if we can draw this out. So Grant is here. He's inside a cannon, and he just got shot out. Boom. And so we actually know the resultant vector already. We know what's happening here. It is 67 miles per hour. That's how fast he's flying through the air initially. And we have, ooh, this is a little different. So instead of saying north, right, north 30 degrees east, what we have is we just have an angle from the horizontal, which is from the positive x axis. All right, so if that's the case, we got to figure out some other stuff here. I want to know how to get this component. I want to know how to get the x-axis magnitude and then the y-axis magnitude, or the horizontal component and the vertical component. So we have to go back to our textbook. Inside the textbook, I do not know what page it's on, but we should have something that looks like this. Horizontal vertical vector component says if I know the resultant vector, I can get the x or the horizontal vector by taking the magnitude of v and multiplying by cosine. If I know the angle, that'd be great. I do the same thing for y. So to get the vertical component, I take the magnitude of v, multiply the sine of theta, and done. If I ever want to get back to the resultant vector, if I did not know how fast it's going, then I can just do this right here. So this is magnitude of the horizontal squared plus the magnitude of the vertical squared. Add those up, take the square root, and you can notice this is Pythagorean theorem all over again. Right there. All right, so let's figure this out. Ooh, you know what? We have to figure out 2 here. So I'm going to do the work on this slide. So Grant was shot like this, I believe. Yep. 67. And this was 60 degrees. So let's go with it here. So the horizontal component would have been, oh, we already know the magnitude. Magnitude was 67. You know, cosine is 60 degrees. All right. Guys have to figure that one out. And I don't have my calculator with me here, so how about this? Can someone in the class do this and just give an answer for 67 times cosine of 60? And then the vertical component. So that would be the horizontal vector. The vertical vector is going to be 67 degrees sine of 60 degrees. And again, someone, if you have it, please tell the class what you guys got. And see if someone says the same thing as a second. Thank you. Hopefully I timed it right. All right. Example 3. So instead of shooting Grant, we have Cat shot an arrow into the air. So its horizontal vector is 30 feet per second. Its vertical vector is 20 feet per second. Can you find the velocity of the arrow itself? So notice that's that little third formula we were talking about. All right, so let's draw this out. This is the exact sort of opposite of what we were just doing with Grant here. So what we do is we know what happened here. We know it was shot horizontally at 30 feet per second because we can measure the distance on the ground. This is more like having a camera that's maybe a satellite image that's pointing down. Then you can tell how fast it's going sideways. We also have another camera image on the side that says, I can see how it's going, the vertical aspect of it here. So 30 feet per second horizontally, 20 feet per second vertically. I need to know the velocity of the arrow. Let's go with it here. I think it's this little formula right here. We take the vertical component squared, or the magnitude of the horizontal squared plus the magnitude of the vertical squared. Putting that all together, and I got a big number, right? 400 plus 900, which is 1300. Is that right? Something went wrong here. Let me just check. All right, I just had to check that on the calculator here, and it looks like, yes, 36.0555. So 36 feet per second is our magnitude right there. So let's also figure out the angle measurement as well. Let's see if we can do that. And so if we're trying to draw this triangle as a triangle, notice this little 20 feet per second, the vertical magnitude, I'm going to switch it or kind of move it over to the right side to form my little triangle. Let's see if that makes sense right here. So my horizontal is here, my vertical is here, and then my resultant vector is going to be right here. What I need a right triangle for trigonometry here. So 30, 20, angle measurement, and again we need tangent because I know the opposite over the adjacent. Let's go with it. 20 over 30. Let you guys catch up here. You guys punch that into your calculator. Tangent inverse of 20 over 30. And if you punch in tangent inverse of 2 over 3, that's still the same thing. It's going to give you the same answer. All right, and we got ourselves 33.7 degrees. Hopefully you guys have the same. So final answer here in a little sentence here. The arrow, or we can say Cat shot the arrow at 36 feet per second with an angle of elevation of 33.37. Notice that we're not looking at, we could do angle of elevation as well. Right, so we have the coordinates of, south 33 degrees north, or whatever you want to say it that way. Let's do that. Let's if we can say angle of elevation. That's one way to say a vector or how fast something is going, direction and magnitude. We could also go back to here, right? And we could say the angle is headed a certain direction, and it is north. Got to get the complementary angle again. There it is. So I got 3, I got 6, and I got 5. So north 56.3 degrees east. Is that right? Okay, so then the question comes in, Mr. NGF, when do you use this, and when do you just give feet per second in that? This one is used whenever you have direction of something. A boat would be a great example, right? An airplane, maybe. So that's when you're just shooting an arrow up in the air and you're coming back down. We generally don't need direction of an arrow being shot. That's going to go up and then it's going to come down. So that's kind of the difference between the two. All right. Let me erase all this ink stuff. And I did want to give you just a quick little thing about tangent inverse. It was not explicitly stated in the textbook here, but if you need to know the angle, you can always do this here. You take the magnitude of your vertical component divided by the magnitude of your horizontal component, which gives you tangent theta. So if you want a little equation to go along with things, there it is. All right, one more thing we have to do is called force. So real quick here, I'm going to read it as you guys read it with me here. Another important vector quantity is force. Da, 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 da. We can loosely define force as just a push or a pull on an object. So the most intuitive force in our lives is the force of gravity that pulls us down towards the earth. The magnitude of this force is our weight. So the direction of the force is always straight down towards the center of the earth. So although there may be many forces acting on the object at the same time, if the object is stationary, so if it is not moving, the sum of all the forces must be 0 or the 0 vector. Haha. There it is. Connect. Everything is all connected. It's the strangest thing. Okay, next. Just to give you that little concept of the 0 vector here, it's the static equilibrium point, which means something is not moving at all. All the forces are canceling each other out so that whatever that object is staying at one spot. All right, so let's do, I think I have 2 examples in the time remaining here. So Danny is 5 years old and weighs 50 pounds. He is sitting on a swing when his sister Stacy pulls him, and the swing back horizontally through an angle of 30 degrees and then stops. So right before she lets it all go. Question is, find the tension on the rope of the swing and the magnitude of the force exerted by Stacy. So how much is she pulling and how much there's tension on the rope. So if you think about it, this is the little drawing here. He was here before. Stacy pulls him back 30 degrees. We need to find T, because that's the tension on the rope itself. And then Stacy, her force right here defined as H. Right, she's the one pulling this back. She's the one exerting this force of pulling back. And then we still have weight of Danny to the ground. So let's see how this all works. So if we think about all these different tensions, there's tension on the rope, there's Stacy, and there's a weight of Danny. Let's try to draw this as a triangle, preferably a right triangle. Can we do that? A right triangle. So if I do this, I'm going to draw it kind of like this. I'm going to go my tension, it's going to be my hypotenuse over here. Then what I can do is I can bring my horizontal piece, my H piece, down this way, and then my weight can go down like this. Are we good? Is that a right triangle? And in fact, there's my 30 degrees right there. So I have redid all these forces so they all connect together. And if they all connect together back, then I know I have an equilibrium point. So everything adds up back to 0. So if I start here, my right triangle, I have H, I add T to it, I add W, and I get back to here. All right, so let's go with it here. Let's start plugging away. We need to find T, and we need to find H, and we need to find the magnitude of those. So what's the tension on the rope? So let's bring this up so I can get more room here. There, and there. All right, what do we know? What do we know from Danny weighs 50 pounds? So I have magnitude of W is 50. And I think that's all I need. I think that's all I need. In order to get T, so let's talk about T. T is here. T is the hypotenuse. W is the adjacent side to 30 degrees. So I think I'm going to use cosine. That adjacent hypotenuse connection. So cosine of 30 degrees is equal to the magnitude of W. Adjacent hypotenuse is magnitude of T. And then the other thing is, I do know what magnitude of W is. I just need to figure out magnitude for T. So how about this? How about we multiply both sides by magnitude of T, and then we divide both sides by cosine 30. So multiply and divide, and we get ourselves this. Magnitude of T would just be 50 divided by cosine 30. Punch that into your calculators. Go for it. And we get ourselves something that looks like this, hopefully 57.7 pounds. So the rope has to hold up 57.7 pounds somehow, at least that, from Danny not to fall off on it. Okay, so now let's go with Stacy. What's the exertion that's happening sideways? Because remember, she pulled him sideways. So how about tangent of 30 degrees? Would you guys agree with tangent? Tangent would be something I know over something I don't know. So opposite over adjacent. Now the question comes up, can I use T? Could you use sine instead of tangent? Yes, you can, except remember how we talked about earlier in class? Is the fact that you don't want to use values that you've already approximated. So if you can stick with values you know initially from the problem, or exact values, those are the ones you want to use. So there it is. Tangent is opposite over adjacent. I do know what W is again. So that's going to be H over 50. So in this case, I'm going to multiply both sides by 50. And all yours, punch that into a calculator. Tell me what you get for the magnitude of H, or the pull that Stacy has on Danny. All right, and hopefully you guys got something look like this, 28.9 pounds. So there it is. So for all forces to be equal, she's not letting go of Danny, she's holding him in that position. All these forces, there's your value on it. So this works in mechanical engineering all the time. You're looking at forces, you're looking for something that is stagnant. So then you're looking at a light pole, for example. Right? You can figure out all the forces acting on the light pole, and then what you also start doing is you start figuring out what kind of metals you need, whether a rubber washer would work in this case, as opposed to do you need a metal washer in order to fix the solution. How far do you extend the angle before it's too much and it's going to cause problems later on? So all those pieces kind of flow into this. All right, we have one more example. And this is work applied. So how much work is done if an object is giving us so much force for a duration of time or a duration of distance. So notice it is just the magnitude of some kind of force, it's cosine of that magnitude, and it's just times your distance traveled. That's how much work it is. So, example here, Mr. T. Mr. T. I don't know if you guys remember Mr. T from the A Team. It was a series in, I don't know, probably early before your time, 1980s. It was Mr. T and the A Team. Okay, look it up if you're curious. Let's go with it here. He's pulling 2 elementary school kids in a wagon at a force of 25 pounds on the handle at an angle of 30 degrees with a horizontal. So how much work is done by Mr. T if he pulls them 350 feet? So let's see. Let's make our little triangle out of this here. So there's my 25 pounds pull because he's pulling the handle of the wagon. It's a 30-degree angle, and he's going to pull it 350 feet. So I guess what we need to do we need to figure out the horizontal component of this. We need to figure out this piece right here. How much is he exerting force horizontally? And so if we do that here, it's going to be cosine. First of all, let me back up a little bit. It's going to be cosine of 30 degrees adjacent over hypotenuse. So there it is. Changing things around. Multiplying both sides by magnitude for f. So the work that is done is going to be the magnitude of f cosine of whatever degrees times d. I think we have all the components we need. So 25 is what we need to put in for the force that he's pulling the wagon on. Cosine of 30 degrees is the angle, and he does it for 350 feet. And that's it. He's tired after that. But the work that he's done, multiplying all that together using a calculator, go for it. And winds up to be 7,600, and we call foot-pounds. That's what, in this case, that's what we call work right here. There's none of the feet that he's carried with the pounds that he is exerting a force on it. So 7,600 foot-pounds of work he did, and then he's done. All right, hopefully that helped. Hopefully we're done, and we have finished up 2.5. I wish you guys all a good weekend, and I'll see you guys on Monday.